reactants. The idea behind this is that we're not always reacting with a set amount of one reactant in excess of another. We're going to start with set amounts of each, and one is always going to end up running out before the other. So a good visual representation of what this looks like is, let's say that we have 8 car bodies available to us and 48 tires, and we want to see how many cars we can make. Okay, each car needs 1 body, it needs 4 tires. So if we use those things up, we've got 8 total cars that can be made. Using those 8 car bodies, we end up using up 32 tires. So we have 16 tires left. So what our limiting reactant there was the actual car bodies. The limiting reactant is going to be that reactant that determines the amount of products that can be made. And then our excess reactant is any leftover. So another visual representation for you, I just find these really helpful. We've got this where you have blue and yellow molecules. Okay, now after they react, okay, you can see all those yellow molecules got split up and reacted with the blue, but you've got 1 blue molecule left over. So since all those yellows got used up, those would be the limiting reactants, and then the blue is the excess. So how we're going to identify some limiting reactants is we're actually going to convert each reactant to grams or moles of a product using stoichiometry. So we're going to use that dimensional analysis setup that we've been using for this entire unit. And then we're going to say that the reactant that makes the least amount of products is the limiting reactant. Now, if it doesn't specifically tell you to go to grams or moles, and it doesn't ask you to find percent yield, I would just go to moles. It's less work that way. Okay, so best thing to do here is start off with a sample problem. So what we have going on, we have 25 grams of phosphorus reacting with 50 grams of oxygen. We need to know what the limiting reactant is. Okay, so what we need to do is just figure out which one of these we want to set up first. Okay, what's nice is each one of these conversion factors is going to look exactly the same. So I'm just going to start with phosphorus. Okay, I'm going to draw out my roadmap. I've got that 25 grams. Okay, I can figure out how many moles that is. Okay, and then I'm just going to take it to moles of our product. Okay, what I want to do is end with moles of the same thing. Okay, and for my second one, I'm going to start with 50 grams of O2, and I'm going to go to moles of O2 and then moles of that P4H10. So setting up this conversion factor, we've got 25 grams of P4 and then why did I make that so long? Now, molar mass for phosphorus. Is, I gotta have my periodic table here, 30.9, so 31. So if we multiply that by 4, that's going to be 124 grams. Okay, So multiply across the top, divide by what's on the bottom. Okay, and then, like I said, we essentially have the same thing set up for that O2. So as long as you do this first conversion factor right, your second one should be pretty easy to fill in because you're going to essentially replace your one reactant with this other reactant. Okay? So I'll put grams of O2 on the bottom here. And molar mass of that is 32.0. Coefficients, we've got 1 in front of that P4O10, 5 in front of the moles of O2. Okay, multiply across the top, divide by what's on the bottom. Clean all of that up. Okay, multiply that through. We should get 2.02 moles produced from this P4. And we've got 3.13 moles produced from the oxygen. So it wanted to know what's the limiting reactant. Now remember, it's going to be the one that produces the least amount of moles. So P4 is the limiting reactant, okay? And that's what you need to put. You need to put some indication that that's the limiting reactant. So I put P4LR. Okay, O2, excess reactant. Once again, you could write that out, but I'm a lazy chemist. I abbreviate everything. Okay, next sample problem. A 2-gram sample of ammonia is mixed with a 4-gram sample of oxygen. How much NO is produced, and which is the limiting reactant? Okay, now, if you're snarky, you could say all of the no, but I'm going to pretend that you guys are not snarky and you do actually care about this. Okay, so I'm going to start off with setting up this one for ammonia, and then just like this last one, we're going to follow it out the same. And it asked how much NO is produced. It doesn't say what mass of it, so I'm just going to carry it to moles. I'm just going to do as few steps as possible. So I'm going to start with 2 grams of ammonia, like it says. And we're going to go from grams of ammonia to moles of ammonia. Carry those grams on the bottom so they get canceled out. And then from moles of ammonia to moles of NO. Okay, always use 1 mole with your molar mass. 17.0 is your molar mass of ammonia. Coefficients with this. Okay, if we're multiplying by 4 and dividing by 4, that's like multiplying by 1. So we actually have 2 divided by 17. That'll be our final one. And then, just like I said the last time, if this is set up correctly, then you just have to replace stuff with your oxygen. So I'm going to move it to the next slide where I should have this set up. Okay. We're going to multiply across the top, divide by the numbers that are on the bottom. And there we have it. 1.118 moles and 0.1 moles of NO. So we are going to produce this 0.1 moles of NO, and since it specifically asks what's the limiting reactant, O2 is the limiting reactant. Since it specifically asks which is the limiting reactant, you've got to indicate that that's the limiting reactant in some way. Okay? You could also come up here and just write O2, okay? But in some way you have to call it out. If you don't call it out, that's an easy point that you miss, okay? Okay, so that is it for today. If you have any questions, please let me know. And as always, you can check your work with the key that's at the